Right. Good evening. So this is Mechanical Engineering 3803, week 11. Our agenda today is on combined loading. So far we have learned that normal stress, is equal to minus px over a plus by my over iyy multiplied by z plus, or it can be minus. Okay, don't worry about the sign. Okay, just writing a general formula, minus mz over izz multiplied by y. Okay, so we know that that is the formula for normal stress. And then we also have what we have is the general formula for shear stress. Right, before we go on, we know that this over here is due to axial load. And these two over here, these are due to bending moment. Another general formula that we have seen, which is shear stress, which is equal to Tx C over J. Then we have Vy over Izz. This will look very familiar to all of you. Divided by T plus by Vz over Iyy Qy divided by T. Okay. So we know that this over here is due to the torque, and this term over here is due to the shear force. Okay. So now the thing is, we need to identify, right? So we need to identify whether the loads, loads acting on the structure is inducing a shear force, is it inducing a bending moment, is it inducing a torque, or axial load or axial force. Okay, so what do I mean by that? Right, so if we look at a example over here, okay, the first example over here, let's look at this structure over here. So this is a true 3D problem. Okay, in real life you don't get 2D problem. Okay, you get a real 3D problem like what you see over here. Okay, like what you see over here. So you can see this load over here has 150 pounds applied at a certain distance from over here. You have 150. Then you have 50 pounds over here. You have 150. You have 200 pounds. So are these loads inducing a shear force, an axial load, bending moment, or is it inducing a combination of bending moment or shear stress? Okay, so I'm going to do this as I'm going to work out on this example, okay, to help you or to teach you how to identify whether is it inducing a combination of axial force and bending moment, or a combination of shear force and bending moment. Okay, so we are going to look at a structure like this. Okay, so I want you to focus on this figure over here, and we want to find the stress state at element H and K. Okay, so this is element H and K over here, as you can see. Okay, so the first thing, once you have identified, okay, element H and K, so step number one, you have to do this step. Okay, I'm going to write out the procedure what you must do first. Okay, you have to, step number one, you have to construct, or you have to, if it's not given, you have to construct the global transformation. Okay, so this is given. What do I mean by global transformation? So you know that this is the X direction, this is the Y direction, and this is the what? Z direction. So you know that this is your X. Sometimes, like for this question, it is given, but if it's not, you have to determine. Okay, so this is the X, this is the Y, and over here, this is the Z. Okay. Then step number two, you have to identify the centroid for elements H and K. Now, this step is really, really important. Okay, so you look at element H and K. H and K are on the more on the horizontal component of the shaft. So you have to define where is your centroid relative to the element. Okay, so this is the centroid. So I'm going to sketch the centroid now. So this is the centroid relative to elements H and K. Okay, now this is a question that we're trying to solve. So we are guessing, okay, element H and K is the point of failure. Okay, some problems later on, when we are maybe in 2 weeks time, you have to identify where the elements is. Okay, so I'll take note, the elements are usually the elements are usually located at positions where failure will occur. Okay, if it's not given, but if for this problem is given, okay, you know, if it's not given, it's always the location where failure will occur. So if there's no element over here where failure will occur at the fixed end. Okay, that's where failure will occur. But this problem over here, they say, the question says, the question says identify the normal and shearing stress of element H and element K. For this problem now, I'm going to teach you how to identify what are your forces, what's your axial force, what's your bending moment, what's your torque, and what's your shearing force. Okay, right. So remember, this is a 3D problem, and our paper is 2D, so we have to solve things in a 2D manner. Okay, and I've identified a way of solving this that is, you will not make mistake. Okay, I've done a lot of this over my years of teaching and also for consulting, and with this technique that I have developed, you will not make mistake. Okay, but you have to pay attention. Okay, now, so what we're going to do now is, based on this transformation, I'm going to view this in the XY plane. Okay, so I'm going to change my paper. Okay, so now I'm going to view this structure over here in 2D now. Okay, so this is our X, and this is our Y, and this is our rotation about Z. Okay, so when we have that, I'm going to make this a smaller figure so you all can see what I'm trying to draw. Right. So what we have is, so we're viewing from the side view now, okay, or the XY plane. So this end is built in. Okay, it's built in on one end. So let me have some. So we have our, okay, so this is 2, 4. Okay, so this is our end over here, and then you have to now draw your elements. Okay, where the element is. So over here, we know that this is our position of our element K. And over here is our element H. Okay. And then we have a vertical. So as I say, this is a sketch. Yeah, I beg your pardon. I have to change this to black. Okay. Then we have to sketch also over here. When you have a view like that, you have to sketch your centroid relative to the elements. Okay, so this is our centroid relative to the element. Okay, there is our centroid. Then once we have our centroid, we put in our forces. Okay, so we have 150 acting over here. And then we have a 200 coming in or coming towards us. And then we have 50 going away from us. And then we have a 150 going away from us. Okay, so you can more or less visualize this. Okay, so step number 3, what we are going to do now is, we are going to step number 3. Okay, so step number 3, let me go back to, I don't need to draw it. So step number 3 is, do not analyze the dots and crosses. Okay, don't analyze the dots and crosses. Just bear with me. Okay, just bear. Don't analyze the crosses. Right. So now the first thing is, we know that there's a moment acting in our z direction. Okay, so we are going to take positive. Okay, we are going to take positive, right? going this way. Now, this is not static analysis, okay? So we are going to analyze all the forces relative to element H and element K. Okay, so the relative everything we are going to reference is element H and element K. Right. So now we know that there's a moment. So the only force that we have to be concerned now is the 150. Okay, for now, because it's not a cross nor dot, it's a complete arrow. Okay, so from here, you know the mz will be equal to 150 multiplied by the perpendicular distance. Okay, so the perpendicular distance over here, take note, okay, the perpendicular distance is to the centroid. So this is the perpendicular distance is to the centroid. Okay, right? So 150 multiplied by 10. Anything else? Nothing else. So it's 1,500 pound-inch, and it's going in this direction. Okay, so now we can construct, right? So this is our moment in Z. And like what we have learned before, the head of the compression arrow is compression. The tail end is what? Tensile. So from here, you can immediately make a decision already. Okay, you can make an analysis. So what is the analysis you can make? You know that element H will be tensile, which is positive stress. And we also know that element K is equal to 0. Okay, element K will be equal to 0. Why? Because element K is on the what? Centroid. Right? Just to quickly recap, if we just focus on moment about Z, okay, so moment, so stress in the X direction is equal to minus